Hey everyone, welcome to this explainer. I'm absolutely thrilled you're joining me today because, well, we're tackling what is arguably one of the most brilliant concepts in all of mathematics. We're going to take the totally abstract world of algebra, all those numbers and letters just floating around in equations, and we're going to translate them into beautiful visual paths. We are demystifying coordinate geometry, breaking the whole shebang down piece by piece so we can see exactly how the math actually comes to life. Let's get into it.
Okay, so let's kick things off with a pretty fundamental question. How exactly do we turn abstract numbers into visual shapes? Really think about that for a second. An equation? It's just a string of text. But geometry? Geometry is all about lines, curves, actual shapes. Coordinate geometry is this incredible bridge between those two worlds. It's literally the mathematical framework that allows us to, well, draw an equation, letting us see exactly what those numbers are doing behind the scenes.
Here is our roadmap for today. 1. Variables, dependent and independent. 2. The Cartesian plane. 3. Plotting points and quadrants. 4. Graphing linear equations. And 5. Slope and y-intercept.
All right, section 1. Variables, dependent and independent.
Let's take a look at the relationship between our two main actors here. Over on the left, we've got the independent variable, which we almost always call x. Think of x as your input. It's like a dial you get to turn. You can choose absolutely any value you want for x. Then, on the right side, we have the dependent variable, usually y. And the value of y depends entirely on what you decided to plug in for x. For example, if we have a simple equation like y equals 3x minus 6, y is the subject. We plug a number in for x, multiply it by 3, subtract 6, and boom, the equation spits out our y. They are totally locked in this mathematical partnership.
Moving right along to section 2. The Cartesian plane, building the canvas. Now, before we look at the whole canvas, we need to know how to pinpoint just a single spot on it, and we do this using an ordered pair. It's simply two numbers written in a very specific order, separated by a comma and wrapped in little brackets, like x, y. The absolutely crucial thing to remember here is that order matters immensely. The pair 5, 7 is completely different from 7, 5. It's exactly like latitude and longitude on a GPS system, right? The first number tells you one direction and the second number tells you the other.
So here it is, the Cartesian coordinate system. It's made of two mutually perpendicular number lines. You've got the horizontal line, the x-axis, stretching off infinitely to the left and right. And then the vertical line, the y-axis, stretching infinitely up and down. Right where they cross, dead center, is that point of intersection we call the origin. Its coordinates? Just 0, 0. Every single point we will ever plot is measured starting right from that exact center origin.
Which brings us to section 3. Plotting points and quadrants, navigating the map.
As you can see, these two intersecting axes cleanly divide our flat canvas into 4 distinct sections, and we call these quadrants. Starting from the top right and moving counterclockwise, we've got the first, second, third, and fourth quadrants. Now, because the x and y axes both have positive and negative sides, every single quadrant gets its own unique sign convention. In the first quadrant, both x and y are positive. In the second, x is negative but y is positive. Down in the third, they're both negative. And over in the fourth, x is positive but y is negative. This is brilliant because it gives us an instant shortcut to know exactly which zone our ordered pair lives in.
So, how do we actually go about putting a point on the board? Well, it's really just following 3 logical steps. Step 1. Always start at home base, the origin, 0, 0. Step 2. Read your x-coordinate, also known as the abscissa. If it's positive, you walk right. If it's negative, walk left. Stop right there. Step 3. Look at your y-coordinate, the ordinate. From where you're currently standing on the x-axis, you just move straight up if y is positive or straight down if it's negative. Once you finish that movement, you place your dot. And that's it. You've just plotted a point.
Okay, section 4. Graphing linear equations, connecting the dots.
Let's contrast some super simple equations with full linear ones. Check out the equation y equals 3. Notice how it forms this perfectly flat horizontal line just floating 3 units above the x-axis? That's because no matter what x is doing, y absolutely refuses to be anything other than 3. But when we look at a full linear equation, something like y equals 3x minus 4, both x and y are interacting. They're changing together. The resulting points form this really beautiful angled straight line. And anytime an equation graphs as a straight line like this, we officially call it a linear equation.
Now for our final section, section 5.
Slope and y-intersect, measuring lines. Let's start with that slant. The angle a straight line makes with the positive direction of the x-axis is called its inclination, and we denote that with the Greek letter theta. But in algebra, we tend to use a concept called slope, or gradient, which we represent with the letter m. The slope is quite literally the tangent of that angle of inclination, so slope m equals tan of theta. Now think about it. If a line is totally flat, parallel to the x-axis, its angle is 0, so its slope is 0. But if it's a straight vertical wall, parallel to the y-axis, its angle is 90 degrees, and its slope is actually mathematically undefined. No way around it.
Okay, so the slope tells us the steepness of the line, right? But where do we anchor it? Well, that's exactly where the y-intercept comes in. The y-intercept, which we usually denote with the letter c, is simply the distance from the origin to the exact spot where our straight line cuts right through the vertical y-axis. If the line cuts above the origin, c is positive. If it cuts below, c is negative. Essentially, it gives our line its starting height.
Now, sometimes you're handed a messy, jumbled general equation, something like ax plus by plus c equals 0. How on earth do you find the slope and intercept from that? Well, you just follow these steps. Rearrange the algebra to isolate y all by itself on one side. Once you do that, your equation magically transforms into that famous format, y equals mx plus c. In this setup, whatever number is glued to the x, the coefficient, is your slope, m. And the number sitting all by itself at the end, the constant, is your y-intercept c. With just a tiny bit of algebra, the equation practically draws the line for you.
We've covered some incredible ground today in this explainer, from independent variables all the way to mapping straight lines using y equals mx plus c. But I want to leave you with a bit of a provocative thought. We've just built an entire visual universe using only two axes, x and y, creating a perfectly flat 2D plane. But we live in a 3D world. What do you think happens if we add a third number line, a z-axis, coming straight out of the screen right at you? How would equations change if an ordered pair became an ordered triplet, x, y, and z? Keep that question rolling around in your head as you continue exploring math, because the tools you learn today, they are the exact same foundation used to map 3D space, video game worlds, and literally our universe. Thanks for hanging out with me for this explainer, and keep learning.